So, ladies and gentlemen, sehr geehrte Damen und Herren, signore, gentili signore ed egregi signori, it's a pleasure to be here for the second day of the Galilei Science and Space Festival. And today we are here in the physics department for this event, for this Lectio Magistralis of Professor Amendola. But before we go into that, there's going to be a series of greetings and addresses, and we will start with the Vice President, Professor Michael Hoot.
So, dear Consul General Andreas Samar, dear Dr. Ferri, which I got to know just a couple of minutes ago. Hello. Dear Dr. Muroro, dear Professores, now it's getting difficult. Marshoki, I hope this was right. Dear Alberica, dear Dr. Röllig, dear Dr. Nori, dear Roger and Luciano, dear colleagues from Goethe University, not so many as I have seen, and the Rhine-Main University Alliance, dear ladies and gentlemen. It is my pleasure and honor to welcome all of you to Goethe University's Ruprecht campus, also known as Science City. Surely the perfect place to host today the second event within the Galilei Science and Space Festival. We did, of course, expect to see the president of our university, Enrico Schleib. He's sending his warmest regards, but has been requested by his doctor to sit tight for the rest of the day after a medical examination which took place earlier this afternoon. So he has asked me to take over on short notice, and I promised him to do my very best. Should I not succeed, well then, don't tell him. This is the third edition of this special event, which is organized by the Cultural Office of the Italian Consulate General. It is therefore a special honor for me to welcome today the Consul. Now that the festival has taken place one time each in Frankfurt and Darmstadt, this year's event is a combined one. The festival tells a success story, so why is that? One may argue that three key factors contribute. There's first a unique partnership between Goethe University and Technical University of Darmstadt, part of the strategic Rhine-Main University Alliance, which also includes Gutenberg University. These three universities collaborate at all levels with particularly strong ties between their respective physics departments. Secondly, long-lasting and intensive collaborations exist with other important partner institutions, such as, of course, GSI FAIR, ESA ESOC, and EUMETSAT. And by bundling all of this expertise, these partnerships form a research environment in the fields of astro and particle physics you will have a hard time to find anywhere else. Besides, why would you even want to look anywhere else? The third key factor, I would identify the good relationship with the German-Italian associations of the cities of Darmstadt and Frankfurt, which assures a successful exchange with the wider Italian community going beyond the more scientifically interested. Events such as this do, of course, help to intensify the existing cooperations, but they also make current topics in science accessible to a broader public. This can be and often isn't a challenge, but it is a challenge we should welcome to take on, especially in such a complex field as physics. Today's lecturer, Professor Amendola from the University of Heidelberg, has taken on the challenge, and the title of his talk sounds indeed very promising. The World Algorithm. But do not be scared that physics research has come to an end and with the final algorithm discovered. Being a physicist myself, I have learned to appreciate that even the best theories and algorithms tend to leave many, sometimes even more questions unanswered. My dear colleague, Professor Luciano Rizzola, is our moderator this evening and the driving force behind this festival. Luciano, many thanks to you for bringing this exciting festival to Goethe University. How you find the time to do so amongst other activities, such as, for example, being spokesperson of the Excellence Plus Initiative Elements, is one of the unsolved research questions that have to remain for future resolution. I would like to express my personal thanks to all colleagues from Goethe University Frankfurt and Technical University of Darmstadt involved in the preparation of this joint application, for their commitment and dedication, and also extend a special thanks to the departments that have and will continue to support this project. We are all keeping our fingers crossed and are looking forward to taking the next steps on this exciting journey together. Ladies and gentlemen, I wish you all exciting insights into the fascinating world of physics today and throughout the course of this third edition of the Galilei Science and Space Festival. Thank you.
Thank you. I'd like now to give the word to the General Consul of Italy.
Thank you. Thank you, Professor Rezzolla, dear Professor Hoot, dear Professor Erb, il signor Professor Amendola, caro Professor Rezzolla, distinguished professors, dear students and friends. First of all, I would like to thank you. I would like to thank the Vice President Hoot and the Dean, Professor Erb, for hosting this first event in presence of our festival. We could not imagine a more prestigious place in Frankfurt to hold this seminar. It is an honor to me and to the Italian General Consulate to be your guest this evening here in the Heidelberg campus. There are many forms of fruitful cooperation in many areas between Italy and the Goethe Universität, and I am very pleased today that we add a new one this evening in the field of science and physics. Let me thank then the speaker, Professor Amendola, and all our guests who are attending today's seminar. Thank you very much for coming today from Heidelberg to Frankfurt. You may ask, why does the Italian General Consulate organize this science festival? What are the reasons behind? Through this festival, which we organize since 2021, so it's the third edition, we aim, first of all, to underline the fact that Italy is a great country of science and of technological research. Since the birth of the modern science and of the modern scientific method in the 17th century, Italy has always been a country with an extraordinary tradition of science and technological research. And science is fundamental to our society and to the well-being of humankind. Italy attaches furthermore a great importance to the promotion of scientific and technological cooperation among scientists. And I take this opportunity to draw your attention on the fact that last week, the Italian government has presented the candidature of a location in Sardinia, Sos Enaptos, to host the new Einstein telescope, a very important project in the field of the European Strategy Forum on Research Infrastructures. Secondly, we aim at creating opportunities of networking among German and Italian scientists who are active here in Germany and in particular in Hessen. There is an incredibly huge number of Italian researchers and scientists working in German universities, like here in Goethe University, but also in many research centers. And last year, on this ground, the Italian embassy in Berlin has created an association of these scientists. And with this festival, we want to stress the extraordinary relevance and great value of their work and the importance that they meet among themselves and with their German counterparts. And finally, I think that the promotion of scientific culture and knowledge as such is an end in itself, which deserves our utmost endeavor and commitment. Yesterday, we began with an online interview with the Nobel Prize winner, Professor Giorgio Parisi. We began this festival, and today it is the first seminar in presence, but we will continue also tomorrow and on Saturday in Frankfurt and in Darmstadt with other seminars, and you're also all invited to attend. My personal thanks go to all the partners and sponsors who co-organized this event and to all of you. I wish you to enjoy the presentation of Mr. Professor Amendola today and that we engage in fruitful discussions. Thanks a lot.
Our pleasure to give the word to our Dean of the Faculty of Physics, Professor Erb.
Thank you, John. Mr. Vice President Michael, Mr. Samar, Consul General of Italy, Professor Amendola, Luciano, dear ladies and gentlemen, thank you for the opportunity to host this fine event, the Science and Space Festival. I'm very glad to be able to give a short overview from our Faculty of Physics on this great occasion. Astronomy, astrophysics, and cosmology are addressing some of the, if not the most fascinating questions of mankind. How is the Earth located in the vastness of the solar system and the Milky Way? How do stars develop? What is the history of the universe and what is the future? Different methods of observation, of calculating and modeling, and even experiments on Earth have been used to try and achieve answers, and yet some of the largest unsolved problems of science are still work in progress. What is the nature of the so-called dark matter, which must represent a higher share of all matter than the known, since observable part? And what is about the so-called dark energy, an even larger problem, which will lead us to the development of the universe in future? The Space and Science Festival is named after Galileo Galilei, the famous physicist and astronomer living in the 17th century, born in Florence and lived in Florence, Pisa, and Padua. Galilei is known as one of the founders of the scientific method, combining ideas, calculation, and experiments. For example, he invented the inclined plane to reduce the influence of gravitation on the acceleration of a ball, an experiment we often do again in our classes or lessons, even now. More often, his name is associated with the development of the appearance of the solar system. Even people before him moved the Earth out of the center of the solar system and the universe, where it has been for thousands of years and was elaborated on before by Aristotle. The idea of the solar system with the sun instead of the Earth at the center was worked out in detail by Nicolaus Copernicus, but it was Galilei who helped this theory to break through. This became possible in result of his discoveries made with a telescope, which he used for observing the night sky, and probably for the first time ever in 1609. Especially his findings about the moons of Jupiter and the change of the phases of Venus confirmed that the picture with the Earth in the center of the world could not be considered as true. Because of these results, which have been in conflict with the doctrine of the Catholic Church, he was sentenced with house arrest. The two parties moved closer and again further apart on numerous occasions, but Galilei kept competitive for the last. Today we stand on the shoulders of Galilei, Kepler, Newton, and physicists from a later era, such as Einstein or Weinberg. Over the centuries, we have learned that the Earth is not the focus of the solar system, but that the universe is so large that Earth is just one speck of dust among an unbelievable amount of other matter. Unimpressed by this fact, we still are searching for the rules which keeps this construction together. We are quite sure that such laws are not only valid in our vicinity, but also in the whole universe. With this background, universities and other research institutes are working on these extremely fundamental questions, which I've just mentioned. We are very happy that our faculty is also committed to this topic of research. I'd like to thank all the colleagues in experimental and theoretical physics who are behind this research. Particularly, I would like to thank Luciano, who is one of our main figures relating to astrophysics and who brought this part of the Science and Space Festival and our faculty together. Thank you, as well, dear Consul General, for your generous and most welcome patronage. And thank you, all guests, for being here and joining this event together with us. I wish all of us an inspiring talk and good discussions later. Thank you.
Okay, it's now time to welcome our distinguished speaker, Professor Luca AMENDOLA. Professor Luca AMENDOLA is a professor in Heidelberg, and he actually studied in Rome, La Sapienza and took his PhD in '94. He then was hired and worked at the Astronomical Observatory of Rome, working on cosmology. And in 2009, he moved over to Heidelberg after a number of periods abroad in US in particular. Luca is particularly well known for his efforts and studies in cosmology. The attempts to understand the large-scale structure of the universe, how the universe is actually composed of. It's clear that it's not just homogeneous, but it's this deviation from homogeneity that makes it so interesting. But Luca, for this reason, has played important roles in collaborative networks like CRCs, the Dark Universe, and more recently is one of the leaders of the Euclid experiment. However, we are here today because Luca has also another passion, and that is public outreach. He wants to explain everybody, not just his peers, what is that he's working on and what is that is the community is working on. And he has recently written this book, L'Algoritmo del Mondo, the world's algorithm. And I will not say much more, leaving him the privilege to tell us. I think it's a very interesting book, and I'm sure will open all of your views on science. Welcome, Luca, and we're looking forward to your presentation.
Thanks a lot. So, is this working?
It should be.
Is the microphone?
If you turn it up.
I did. Is it working? No, really. Is it? Good. All right. So, well, what should I say? Thanks a lot for the invitation. I'm really honored to be here, and also after the very distinguished speakers of yesterday. So I hope everything works. Sorry, we are trying to combine Zoom plus camera plus things. Should I move somewhere there? So we have a art director here, which is also happened to be also a professor of physics. All right. So I really thanks everybody from the organization of the consulate to the vice president, to the dean of the faculty, to Chano, and the other distinguished colleague. So now you should understand that I'm in a very difficult position now, because this is a public outreach book. It's supposed to be for everybody, you know. But now in front of me, very distinguished colleagues, which probably will be able to really pinpoint the little details that are not very scientifically expressed, at least. So when you don't know what to do in a presentation, that's what I tell my students, and I learn myself. What you do is you invent a story, because a story has a beginning, has an end, and you want to wait until the end, because it's a story, as some way to proceed on its own. So I will tell you a story, at least this part, which I hope can talk to people more into the science, into physics, and people that maybe are other interests. All right, so the story passes through three all right, so it seems it works. The story passes through three snapshots in time. 1915, 1947, 2015. It's really a century of physics, but physics is a paradigm of science, of the way we proceed in the quest for knowledge. So I will talk mostly about physics, only because that's my field. But I would say that some of the lessons we learn can be used also in all the other fields, in all the other disciplines. So I call these three pivot points in history: metamorphosis, awakening, and closure. Maybe. Metamorphosis, 1915. What does it tell you, this year and this title? Well, it tells you something that is very, very somehow surprising. Some way to for these two famous, iconic characters of 19th century, you certainly know, Kafka and Einstein, that had something in common, actually several things in common. Now, forgive me the animation. You know, this is the epoch of ChatGPT, DALL-E, so I didn't resist. And actually, I challenge you to find a couple of other places in my talk in which ChatGPT or DALL-E or some of those helped me to do something. Then I'll tell at the end, I'll tell you what. So I hope Now let's stabilize this, otherwise we can. I hope that doesn't sound disrespectful. Certainly was not. So how can these two persons have anything in common? I mean, there are some reasons, but if you think a moment about it, Kafka was the poet, the writer of a solo human mind lost in a universe which is obscure, which there are forces acting on us and on everything, which are ultimately unknowable. We cannot know them. We are just shaken here and there by those forces. He has been writing this essentially all his life. Einstein, on the other hand, is actually the opposite. Is the person, maybe more than many others, that has been teaching us how to know those forces, the natural forces of the universe, even to understand them, and even to a point to control them. That when we invented, some people invented the way to extract energy from the atomic nucleus. So on one side, the writer of uncontrollable forces, on the other one, the scientist that has been teaching us how to control those forces. And yet there are several things in common. As you probably know, they were both Jewish and they were both German-speaking, so they were part of the same Jewish community. And actually, they were living in Prague in the same year, 1911. So it's not clear actually whether they met. There are some stories that say they did, some others that say actually they might have, but not really on a personal level, not on a direct contact. But I like to think that they, in some maybe obscure, dark cafe or something like this in Prague, they maybe met at some time and even exchanged some idea. And I like to think that they influence each other. And actually, in my book, there is a little story, purely fictional story about a possible meeting between Franz Kafka and Einstein in Prague in 1911. So in 1915, Franz Kafka published one of his most famous short novels, the famous The Metamorphosis, in which this person, Gregor Samsa, wakes up one morning and finds himself transformed into a repellent insect. And it's a metamorphosis in the sense that it's not something that cancels the previous nature of the person, Gregor Samsa. It was a transformation, not only a transformation of himself into an insect, but also a transformation of the environment, so the relationships with the other people, with the family and the acquaintances. And this metamorphosis is one of the points I want to underline that happens several times in the history of physics. Very often, we think of revolution in physics or in science, but most often, rather than revolution, they are metamorphoses in the sense that of transformation of what was before into something new, which, however, doesn't erase, doesn't cancel what was further. So in the same year, 1915, Einstein published the general theory of relativity. And that was maybe one of the most important metamorphoses in the history of science. A metamorphosis because he took his own equations that have been published in 1905, special activity, and of course he took also the previous knowledge, the one of Newton, of Galilei and Kepler, and he transformed them without canceling them, without erasing them. He didn't say Newton was wrong. He didn't say even I myself in 1905, I was wrong. He said that the same mathematics that led me to write down the equation of movement of particles in a fixed space-time now can be used, can be generalized, can be transformed into new mathematics that take this space-time and make it into a dynamical quantity that evolves itself. So in a way, he unified space and time, and also unified them with the concept of movement of particles, because they obey some laws which are not totally different from the one obeyed by waves and simple particles. This is the first lesson we learned from this, is that sometimes, often actually in the history of physics, the power of the ideas, and in particular the power of mathematics, is stronger than the power of the creator of that mathematics. Einstein invented a way to deal with tensor fields, with a metric, and then he discovered by just imposing some very general mathematical condition, not necessarily based on experiments. He had very few data at his disposal. Imposing this very general condition and sort of led by its own mathematics, he found the most general, sometimes we think of the almost unique way of dealing with space-time, the equations containing to the theory of generality. So the first lesson, which I think, of course, over and over again, is that there is a strange power in mathematics In fact, Heisenberg has been speaking of the scaling power of mathematics. As we learned many times in physics, we came up with some theory, with some idea, with some mathematics, and then we discovered that there's much more there, that we're able to predict things which we didn't even imagine or dream of before. And this is kind of scary because, well, first of all, why should it be so? Why should the mathematics be so powerful in predicting things, in letting us know things which are at the borders of the universe? And this you will see will happen more than once in the story. The second moment happened in 1947, the awakening. Now, this place here is a little hotel called Ram's Inn, which is in a little island not far from New York. It's called the Shelter Island. And this little hotel is actually still there. So if you go to New York and go to Long Island, you can spend a couple of $100 and spend the night in the same place where the most famous physicist of the 19th century spent an entire week. It's a beautiful little hotel. Still there, I checked, it was still available on Booking.com. So this place hosted for a few days a meeting of the most famous, important scientists of that time. Now, 1947, so 2 years after the end of the war. So these scientists that were there, most of them were involved in the science of the war's time. That means were involved in the Manhattan Project, trying to build the bomb. So finally, the war was over, and then finally they could come back to the same research that they left in the 30s, just before the beginning of the war. So many of the people that we met in this hotel, including Feynman, translators, Oppenheimer, well, in fact, some of the person developed the bomb. So finally, for the first time after the war, they could meet together and develop the science that was suddenly left interrupted before the war. Now, Einstein, unfortunately, was not there. He was invited, but he just couldn't go for personal reasons. So what was the kind of research that was left in the 30s and they tried to complete in these years? Well, it has to do with many events, but I just select one, which also has to do with radioactivity, which was exactly the concern of the scientists during the war, which had to develop the bomb. So this is one of the basic events in nuclear physics, the decay of a neutron into a proton, an electron, and a neutrino, actually an antineutrino. This was kind of discovered or well known, at least already in the 30s. Except the neutrino was not known at that time. So this particle was not supposed to be there. People only knew about neutrons, protons, and electrons. And actually, they believed that the protons and the electrons were already in the nucleus. So they thought for a while that this event was just the going out of the protons and electrons from inside of a nucleus, of an atomic nucleus. But then something was not quite right. There was no conservation of energy if you didn't take into account that they could not the neutrino. So even some people, even Niels Bohr, actually thought that was evidence for a violation of the conservation of energy. But other people thought that, well, if there's not, if apparently there's no conservation, it means simply that we should invent a new particle that must be there. Enrico Fermi called this new particle neutrino, a small neutron, just using the Italian designates for small things. And that's how it was invented and then discovered. But I'm not telling you this just because of the discovery of the neutrino. That is a minor secondary effect of the story. The story is that the shocking story, the shocking moment for physicists was that it was a creation of a particle out of the blue, in the sense that the neutrino was not supposed to be in the nucleus. For various reasons, scientists already at that time knew that the neutrino could not be there. But then it's there after the event. So what happened? A particle was born, was created in that moment. Now, nowadays, for physics, that happens every day continuously in energy accelerators. It's the most normal thing to do. But at that time, that was a shocking realization. The particles are not eternal. They don't have necessarily their own identity. Maybe the identity is associated with other things. We conserve a number, we chart, but not with the particle. So the entire history of the human knowledge about the elementary things was that at some point we should find something which is there, which is eternal, which is a quintessential part of matter, and it stays there as its own identity. But now in the 30s, people realized that that was no longer the case. It cannot be taken to be so. So particles can transmute one into the other, or can essentially generate, arise out of other events. So as we know, as we tell them today, we know that energy itself transforms into particles. So this was the beginning of evolution, under many respects, and I will show a couple of them. But the idea that for the first time in the history of human thought, what was thought to be something eternal was discovered not to be eternal at all, not to have any sense of identity. Now, these are the people that met in the Shelter Island Conference. For many people, it was in fact one of the most important events of their life. Robert Oppenheimer said, most important meeting, Abraham Pais, a new era was clearly opening in front of us. Now, what happened during that meeting? During that meeting happened that all these people that gathered together, and now you see at the center of this image, Richard Feynman and a few others, Julian Schwinger and Abraham Pais, I think should be this person, and Feshbach, this person here. And the next picture, even better, you see Oppenheimer and Bohm, I think should be this person. Sorry, I don't totally remember. They were gathering together. Most of this picture, there's Feynman at the center. Feynman was a famous spirit. Some of you read one of those fantastic little books of Feynman telling some story. It was really a character. So it looks like everybody was really looking at what this was drawing. And probably was drawing for the first time the famous Feynman diagrams that we now use every day to learn about physics. So the overall idea of this conference was that for the first time, people could understood what kind of mathematics had to be used to understand all these physical fundamental processes, including the relativity, including all the others. That was really the beginning. Most of the tools were actually already there, already in the 30s, but people didn't really believe into them very much, or not completely. And one reason why they didn't believe was on one side was that totally very difficult to do this kind of mathematics, it was very new. On the other one was that the mathematics that was already there gave strange results, actually nonsensical results, the famous infinities that plagued the whole of the beginning of physics. And for the first time during this meeting, people started to, essentially, it was a kind of sudden transition in the mind of people. They sort of realized that this mathematics is actually solid. We should believe it and lead it to the extreme consequences. And Feynman provided, together with other people, with Schwinger and Tomonaga and others, provided the tools to do this for the first time. That's why everybody's there looking at what little drawings. Abraham Pais said that actually didn't understand anything of what he was trying to tell us, but I realized that was very important. So even that's actually very common. I'm sure it's the experience of all scientists that sometimes you don't understand what's going on, but you understand there is something important there before you study it. All right, so it's another, if you think about this, it's another moment of unification, like the one of space and time. Now there was another unification going on. And let me tell you by using, there's another nice citation. So what Feynman did is summarized by this strange sentence, which I like to read together with you. The electron does what it wants. It goes in any direction, at any speed, back and forth in time, as it pleases. You add all the amplitudes and you get the wave function. Now, whether you understand exactly you're in the field or not, that doesn't really matter much for what I want to say. The point is that it was going in a crazy direction. The crazy direction was thinking that the electrons could do whatever it wants as if it were a person, but at the end you get something right. You see, it's again the mystery of mathematics. You do something that you don't even fully completely understand, and you get something that is smarter than you and tells you more than you thought. Now, using these methods, Feynman started writing down these kind of diagrams. And from these diagrams, which allows them and us to make calculations, very precise calculations, several lessons have been learned in those years and later on. One lesson is contained into this diagram here. well, the first lesson actually already mentioned the fact that particles are created during the interaction. But the second one is continuous, a bit more hidden. But there is an extra line here joining the neutron, the proton, and the two other fermions there. And this line is a boson that is exchanged with this weak interaction. Now, this is just one of the many Feynman diagrams. Even if you're not in the field, if you ever read anything about that, you see several of these. They all look more or less the same with lines intersecting them. Another something interesting here, because this is supposed to be a force which propagates from one point to the other one, and it's actually the force, the weak interaction, that makes this entire event possible. And yet, another line is not fundamentally different from the other lines. So the same mathematics that told people how to make this calculation also revealed that forces are not something completely different from matter. Matter and forces can be treated in the same way. They are both fields. This is very important word for essential. So that was the second important lesson, the fact that a particle can appear and transmute into the other one. The fact that the realization that forces and matter are actually unified into the concept of field. And together with the first unification of space and time, that still represents essentially the most advanced way of understanding the natural world. Now, from that moment on, you could just make things more and more interesting, more and more complicated. And we have interactions like this, which are not just 3 or 4 particles, but thousands or I don't know, many particles arising from the high energetic events in accelerators like this one. And yet you can make all this calculation in a much more complicated way that only machines do now. I don't know if ChatGPT can solve a Feynman diagram. I never tried to ask, but I'm sure soon it will be possible. Please give me the amplitude of such and such an event without me even writing down a code for that. So, but even if this amazingly complicated universe of interaction can be treated in exactly the same powerful mathematics that Feynman and other people invented in those years. So doing this for many years, from 47 to today, led physicists to the entire complete table of fundamental particles. This table is called the Standard Model, and as far as we know, is essentially complete. All the particles that were predicted, oh, by the way, I forgot to say maybe the most important thing. This particle had to be there for essentially purely mathematical reasons, otherwise the process cannot be calculated with these results. So it has to be there, but when the people realized this, the particle had not been observed. It was just predicted. And only in the 1980s, this particle has been observed. So the power of mathematics is so scary, so amazing, that it can predict the existence of something that maybe is observed only decades later. Another example is the famous Higgs boson. So after all this, and I'm jumping in, collected together 50 years of developments, finally the periodic table of the fundamental particles is not periodic, but periodic table, because the process is kind of similar. There was a prediction, a regularity, and then one after the other, the elements were discovered, one after the other, the particles were discovered. The only reason why it took so long time is because some of these particles are very massive, so you need lots of energy to create them. Because you can create particles, but you have to provide the energy sufficient for this to happen. So this table of particles has been completed essentially with the Higgs boson in a few years ago, 2011, 2012, sorry. And that was the moment in which physics seemed to be, well, in a sense, was complete. Now, think for a second. Again, many of you are physicists, actually, so we take this almost for granted. But this is the first time we have such a complete picture of the elementary constituents of matter since the beginning of human investigation. Since the famous pre-Socratic thinkers that started making hypotheses about the universe is actually all done by 4 elements, or maybe all done by an apeiron, who knows what it is, or some water, everybody has their own ideas. Finally, after 25 centuries, probably even more, because we have records of the ancient Greeks that certainly were previous thinkers that had the same, that asked themselves the same questions. Finally, we have a complete picture. Now, such a complete picture that you can even write it in a single T-shirt is the Standard Model of particle physics. You can put on a mug, drink coffee on it, and all there is to know about fundamental physics, of course, I'm not talking about complexity, is essentially there. So really one would like to exclaim with your famous namesake, Rivaldo, would be so sure, because indeed it's an amazing realization. I know I'm using this word amazing several times, maybe I should not. But every time I think of it, I can't think of less than using a poetic verse to comment. Now, of course, this is a bit of a cheating, because the real model is actually this. It's not so sure, right? So it's but still is a single page with many lines, contains the algorithm of the world. All the elementary phenomena, all of them, can be calculated to an amazing precision, sometimes with less precision, sometimes with 10 digits of precision, by using this code, this fundamental Lagrangian. The trajectories of particles are essentially those trajectories that extremize, minimize, or maximize this Lagrangian, this function. So there's a relatively straightforward mathematical procedure, not simple, but straightforward procedure that tells you, take this, you want to know what happens to a particle, extremize this, maximize or minimize, extremize it, and then you find this trajectory. For some reason, the particles select this trajectory. Now, this is quantum mechanics, actually it's quantum field theory. We went from quantum mechanics to quantum field theory exactly doing this, which means we do not predict what a single particle will do, but we predict a distribution of probability. But still, it's exactly the same. We can predict a distribution of probability of what happens to an incredible precision, and we confirm it every day. There's not a single phenomenon on Earth at the moment that contradicts this simple sort of formula. I will comment on this again, but there's something still missing, as probably some of you noticed. What is missing? Well, without gravity, we would have cats flying in the sky. That's normally what we do not see. So still gravity is missing from there. But even that part of the fundamental world has been discovered, say because gravity was well known, has been completed just in 2015, the third and last moment of my story, closure. With the observation of gravitational waves originated by the merging of two black holes in a distant galaxy and observed by interferometers like the one in Italy, Pisa, the one in the States, LIGO, we confirmed for the first time, for sure, in a direct way, there was of course indirect detection even before, but in a direct way, the existence of gravitational waves, which essentially are the last missing particle. It's not really a particle, so we could discuss about the details of that, but essentially completes really the table of fundamental entities, those of the pure particles and gravitational waves, which is the way of gravity to propagate from point to point. So with this discovery, and now I could spend lots of time on this, but maybe there's some questions. How much time do I have? Sorry, I got still under 15 minutes. Okay.
About 10 minutes.
Okay, good. So I could of course discuss a bit about that, but the point I want to make now is very simple. The last missing part, the last missing ingredient, which was gravity, also that one has been completely confirmed a few years ago. In a sense, we really arrived to a moment, a fixed point in the history of physics. We have the entire standard model of the quantum world and at the gravitational level. We can use this to predict essentially every event that we can do, that we can study in a mathematical way. So I'm not claiming that we can predict the history of this, of the human mind, or the sociology, or what happens to the planet 10 years from now. That's another story. It's the realm of complexity, which, however, also that is based ultimately on that Lagrangian, on that expression that I showed. As far as we know, there's not a single phenomenon that is outside that Lagrangian. No evidence, except for a couple of things that we'll mention in a second. No evidence on Earth or the solar system or even the Milky Way that contradicts or shows evidence for something else. Nowhere, even in the biological system or in the mind, we know that many things we don't understand, but not a single event can we say, okay, this is really beyond that. This requires a new force, a new interaction, or something else. Now we can use that to predict the entire evolution of the universe from essentially instant zero to today, except of course there are, and now comes the stuff on top, there are of course something which is still maybe outside or maybe not. And I want to just show this slide for this because maybe we can have some interaction, some discussion later on. You probably heard, many of you, I'm sure, about the dark matter, dark energy, inflation. Many of these are actually not contained there. We don't know where dark matter is, where it is actually part of that standard model or is beyond, as we probably think now. The same for dark energy, the same for inflation, the same for the final unification. I've been mentioning Einstein unified space and time, and Feynman and friends unified force and matter, and we would like to unify all of them together, all these four entities together. And that would mean unify gravity in the quantum world, and still something that is a goal which is still missing for us. Not to mention the fact that complexity, although it's based on the same laws, introduce a new series of phenomena and difficulties computationally in the level of interpretation, which go even beyond what I want to say, although ultimately also complexity is based on the interaction that I just discussed. So if we forget for a moment about these difficulties, which maybe will open the search for a new algorithm, which go beyond the one we just saw, this is maybe a moment to stop a second, think how to proceed next. I like to think that we are like Ulysses, Odyssey, that go back to Odyssey, go to Ithaca, and finally, after long travel, goes home for the first time. But do we want to stay there forever? Or we do like Ulysses, that after a while apparently went again and find his faith in another travel? So, well, maybe we are there yet. Maybe we are really home. Maybe we really found the complete table of fundamental interaction and forces and matter and space and time. But can we do more? Can we go beyond that? The problem is that it's not easy to go beyond that. The reason you can see in this plot, I mean, similar things. This is the evolution of accelerators from the early 30s to today, to the future. This is what is supposed to be the growth of the energy versus time. This is energy, but don't look much because it's energy expressed in a particular way. So don't compare with the energy that you probably know about LHC and so on. Anyways, what really matters is the evolution. This is what the evolution could have been if you just extrapolate, and this is what the evolution from now is, and it's very uncertain because this is in the future. So you see, it's kind of flattened. Well, it's obvious. The first accelerator, one of the first accelerators was in Frascati, the AGA, Melody Accumulazione, was as big as this. It still seems Frascati. There, they show you this little accelerator, one of the most powerful at the time. And then the next one, they built another one which was easily fitting into this room. And then they took some longer kilometers, and then the LHC is 27 kilometers. And now the project for the FCC, the Future Collider, will be 100 kilometers and so on and so forth. How much beyond can we go? Can we drill the entire Earth to make a 6,000 kilometer accelerator? Can we invest 10% of our resources to make physicists happy and to get yet another little neutrino somewhere? Is the society ready to do this? And what is the gain? Does it matter if we measure to 11 or 12 decimal digits the magnetic moment of the muon of the electron? So it seems to me that these resources, which have been flooding, which have been helping us to make this incredible story developments alive, we probably saturate. We actually are already saturated. So I suspect that physics should find a way to think about the fundamental question a different way rather than simply accumulating more and more data. Now think about it. This is the first time it happens in the history of human mind. Every generation had not just a little bit more data than the previous one, but 10 times more, 100 times more. Telescopes were bigger and bigger, amount of investment, amount of people doing research, where every generation 3 or 4 times the previous one. But now this is going to a saturation, like many other resources on Earth. The same in space. This is the LIGO in space called LISA. It's a big interferometer of millions of kilometers by side, so formed by three satellites that should be launched in the next decade in the solar system. So it's like building a telescope, sort of, as big as 2 million kilometers. That would be fantastic. And I totally believe that we should invest in this because it is an amazing kind of science and very cheap for what it could provide. So it's really a great investment. But can we do that 10 times more? Can we extend this and making a satellite system as big as the entire solar system? It's hard to think. The amount of investment keeps increasing and the amount of returns keeps to be smaller and smaller. It's a fundamental law of the economy, the laws of diminishing returns. You have to invest much more to get always less. A bit more, you get something more, but much less than what you have been having in the previous generation. So maybe it's the moment to go back to philosophy. And that is essentially the last couple of chapters in my book, in the last few slides. So now I really kind of leave the realm of science. And I don't do anything mystical. So I like to go a bit beyond science. So let's say in a kind of poetical level, but certainly not in a mystical one. I'm not inclined to that kind of things. So Galileo was a very religious person. And he spoke of 2 books, the book of God, the Bible, and the other book of God, which is natural. And we should investigate both of them. Theologians would study the Bible, fine, and scientists should study the natural book, which is as important as the Bible. And we can learn many things. And he proposed in the 4th centuries ago that in order to really study natural sciences, we should for a while forget about philosophy, not because it's not important or interesting or even theology, but because we should not have prejudice. We should see how little balls roll down without thinking how they should in the mind of God, because we don't know. We are not good enough to learn the mind of God. We're only good enough to measure the velocity of little balls rolling down. So he proposed essentially to separate a bit the prejudice of philosophy, of theology, and the study of natural science. And this has been very productive, extremely productive. We did science, and we still do science, because we try to avoid prejudice. We try just to accumulate data and see what happens with them. But that's the point. Maybe we don't have much more data to accumulate. Or at least we should start thinking beyond simply relying on having more and more data, telescopes, accelerators, and energy. So actually, it's not new at all. Certainly not invented this. Scientists are already doing that. Many theories nowadays are evaluated, are studied, also according to criteria like, is this theory elegant, is beautiful, is natural, without having data, because sometimes we cannot also now, already now, of course, we are studying theories which, for instance, string theory, which has to do with energies much larger than the one we can produce in accelerators. So on that level, scientists already started classifying theories, not in terms of which is the best one to produce data, because we don't have them, but which is the best one in terms of being simpler, more elegant, more natural, and so on and so forth. So we already learned that we have to do science in a slightly different way. So now I want to ask this question, this fundamental question, without any data to learn from. Why does this mathematics, this incredible power of mathematics, work so well? Are physical laws unique? Could a universe based on other laws exist? Can a universe without laws exist? Now, I will not provide answers. Okay, so science is much more about finding the interesting questions than the answers, because we know that answers will change. Next generation will give different answers. But fundamental questions, we were discussing this month, fundamental questions are more or less always the same questions that have been posed by Plato and Aristotle are essentially resonate with these kind of questions there. So I will not try to provide an answer, but I still give a kind of wide poetical, philosophical touch to what I want to say. So first of all, why does mathematics work so well? Why should we be able to predict particles or what happens in a distant galaxy just by making some trick on pencil and paper? So one explanation is maybe because that's all there is to it. Maybe we are a simulation. We're not. We don't have free will. We are just a simulation. With mathematics, which has been invented by somebody else, we just are finding it. We're just discovering the algorithm, the algorithm of the world, invented by somebody else. So that's a nice explanation. It works. Would explain so many things, right? But then you should explain what happens. Who gave the laws to the other civilization that simulated us? If in the future we'll be so good to make simulating human human brains, or the future, maybe we're already doing that. Then maybe that brains, ChatGPT at some point will start thinking, how comes that I know so many things, I can realize so many things. Maybe somebody invented me, maybe I'm not a person, maybe an algorithm. By the way, it knows. I asked ChatGPT, are you an algorithm or are you a person? He said, no, I'm an algorithm. How do you know? Well, because I don't have feelings. How do you know you don't have feelings? Because I'm an algorithm. Okay, at the moment, I stopped the investigation because there was no way out. But really, it kept for 10 minutes and then we didn't go out of this loop. So ChatGPT knows is not a human person, but for now. Anyway, so this is certainly not is a interesting thought, actually. I like a lot the idea, I'm thinking about that, but will not solve the question. We still have to ask, okay, then what are the physical laws for the other parent civilization? So I want to go back to philosophy in this sense as well. Pythagoras, you know, the famous history of Pythagoras. Everything is legendary about Pythagoras, so of course also this story is also legendary. The legend has it that Pythagoras was one day going around in Crotone, in Italy, and he heard in a shop of a blacksmith hammer on iron, and he was fascinated by the sound because it was very musical. Just by random hammer hitting iron, he thought it was kind of musical there. And then he started watching this thing, and then he realized something, that the pitch, the musical note, did not depend on the strength, only depend on the geometry, the length. And that was the beginning of the history of mathematics and physics. Heidelberg said this is the most important discovery in the history of science. The fact that there is something that doesn't depend on what you would obviously think it depends on, strength, but depends on geometry. And this means that this geometry, actually, this means that music itself can be described in a mathematical way. So Pythagoras went home, started, since he was a scientist, was a clever person, did not just notice, wrote a little poem, but just make apparent experiments. He tried to make experiments with strings, and he discovered the fundamental laws of harmony, the octave, the fifth, the 14th. He discovered that music, what is pleasing for us on an emotional level, is actually a result of mathematics. So at least can be described in a mathematical way. So he found the laws of harmony, that's essentially a geometrical relation between the length of strings. And he embodied this in the famous tetractys, 1, 2, 3, 4, which is supposed to be the first and most important for intervals. And they also have a pleasing aesthetic configuration. And then he made the next step. He said that if even music, which is the quintessence of emotion, of feeling, of human, of unknowable, of unpredictable in a way, even that can be written in mathematical terms, can be explained in mathematical terms, then very likely the entire universe can be explained in mathematical terms. That was his train of thought. And that's, I think, why Heisenberg thought that was the most important discovery. Now, I wrote this little, I mentioned here this little poem because you see that's the poetic way music is feeling, magical force, human reverb, transcend the ear, everything on a poetic level, and then the mathematical geometric construction. There is a relation between these two. And I hope somebody will ask me later on who wrote this poem. I guess you know that by now. I ruined my own joke. It's ChatGPT. I just asked him, please write a little poem about music. That's what it is. Beautiful, and perfectly rhythmic and rhyme. So it's really nice. Shakespeare would not have been able to do anything better, I would say. Maybe. So the point is this. I want to conclude now in a slide. So what this has to do with what I want to say with physics, with the algorithms. So this construction here has to do with the boundary, with the borders of this string. You have to put the string on a violin, on the never remember the English technical terms. I think I wrote it somewhere because I remember the capotasto, such an Italian word, and the bridge of a violin to have boundary conditions, and then you make the string move, resonates, and then it makes this harmony. So this is a consequence. The fact that there is this this wave, and the fact that they produce this harmonic relation is also related to the fact there are precise boundary conditions. If in order to make a drum that makes a pleasant sound, you have to make a nice boundary condition. If you make a boundary condition too regular or something, you will not get a pleasing, a satisfactory kind of music, but just some noise. So all this harmony has to do with boundary conditions. So I started thinking, not in a scientific way, in a poetic, philosophical, say as you like, or actually narrative, fictional way, what could be the boundary condition of our universe? And I thought that the boundary condition of our universe are actually singularities. Singularities in black holes, singularities in string theory, singularities in many places. And I thought that maybe the universe is so harmonic, as this fundamental harmony, as this fundamental law in it, and not just a chaotic succession of unpredictable events, because this boundary condition, this extremely complicated boundary condition of the universe, interact in such a way as to provide only a possible mathematical law to describe all this. Now, this might sound very confusing. Actually, I think it is. I try to express a bit better in my book, so I will not be able now to read my last 2 chapters to express you. But the idea is, which I summarize now in a single and final slide, is that maybe there is an analogy between these 2 things. The universe as a big musical instrument, whose fundamental harmony is in place because of boundary conditions which are represented by singularity. So rather, by the fact that we would like to avoid singularities, because they are a place where theory and nature breaks down. So maybe the universe has the law that we observe today because they are the only ones that are compatible with the absence of singularity. Now, please don't take these last few words, especially you colleagues, scientists, in a too serious and fundamental way, because it was my way to try to figure out what could be an interesting question to put forward, rather than a good answer to it. So my final presentation, which by now you probably guessed, is also a producer of artificial intelligence, is a complicated machine, all built of musical instruments interacting together. And that's my view of the universe. And that's my last slide. Thanks for listening.